So today let's continue with Croof, and my plan is to try and add new types. So we'll try to add integers today, and we'll make it possible to parse negative numbers, right? And we have to think about some things like maybe operator overloading. I would like to have that as a feature, would be pretty cool. So that way you don't have to define different names for plus, you can just have one plus, and then you can add easily natural numbers between them and integers with each other, right? So it would be much cooler. So let's try to implement those things today. So first things first, let's go into the lexer and let's add the possibility to parse negative numbers, right? So parsing negative numbers, let's go to, so we have the lexer, right? And here somewhere we should have tokenize number. Okay, so I guess we could disallow negative numbers and just have an operator that converts a number, like a natural number, to integer, but we still want to be able to display negative numbers at some point. So I'd say it still makes sense to parse like a negative number. So let's go over here. So at some point we should see something like if is symbol, right? And the problem with is symbol is it also parses minus. So I would have to move this one up, I guess, right? So it's the first case. And besides, if the first character is a digit, we also have to take into account what happens if self.ch is minus and the next character is a number, and self dot, I think it's called peak, which just shows us the next character. This one, it's weird, it shouldn't be mutable, but whatever. So peak should show us the next character, right? And if this character is ASCII or ASCII digit, then we have to parse a number, or I guess tokenize a number. Okay, so let's go ahead and let's copy paste this entire thing, and let's go into tokenize number, and right here we should add this thing as a check. So if it's not one of these, then it's gonna be illegal token. Okay, makes sense. And then while we are able to parse an ASCII digit, we have to push one of these characters. The other thing we have to do before we start the string is to add another if statement, and if we have one of these characters, or I guess we should just initialize this thing with self.ch. Maybe I have to call into on it or something, and then we have to do self-read. Okay, whatever, I can just push it, right? And then we call a read just to skip this first character because it can be a minus, but after the minus we need to have only digits. So this way we should be able to handle negative numbers. We still want to handle the real numbers or like floats, but that's something we'll see. So let's check in examples. Let's do 05 int dot croof, and let's try to write like a negative number and maybe a positive number and run the lexer on it. So we are gonna use dash, if you use dash help, you'll see that if you use the L flag, it stops at the lexer stage, so we only run the lexer, right? So examples 05 int. So we get a negative number. That's fine. Okay, cool. So what's the next step? Well, in the parser, we don't have to change anything because a number is just a number. There's nothing special to it. But we might need to do some changes in type checking. So right now we only have the type n, but let's add a pub const for type z. Now this one is gonna be obviously z. Okay. I think I want to do them like this because you see the type and then the main function of sook. And I think I want a function to const function z, which what I think this function should do is take a natural number and invert it. Or is it called invert? Invert natural number. Inverse, I guess. No, that's like something else. I mean, you know, getting the like negative. I'm not sure. We can call it z, and this function is gonna be something like takes a natural number and gives us a z number. So but it's also kind of stupid because what can we do with maybe we just want to convert, yeah, let's keep z as a function that just converts a natural number into z number, because you know a number like 1 is both natural and integer, so that would work. And then how we can obtain negative numbers is by adding two z numbers. So if you add -1 plus 0, you get -1, right? So that's the idea. Okay, fine. Anyway, so this is what z is gonna do. It's gonna just convert a number into z number. Okay, perfect. So let's go ahead and let's define the z set. So the z set is just gonna be same thing as the natural numbers. It's empty, right? Perfect. And let's also define the z function. Right. Z function just returns z. Perfect. Function z. So token whatever. Oh, here I forgot to say z. Function z, it takes n and it returns z. Perfect. Okay, so right here we don't define any implementation, it's just like a symbol. And now earlier I was talking about operator overloading or function overloading maybe in the future, and oh, I didn't set the type here. Now last time I said that it's a good idea to always set the types. So right here we have a mapping from a string to a defined node, right? A defined node is just like a function, an operator, or a set. What I think I want to have here is maybe a list or something, because you can overload functions. You can have multiple definitions with the same name but different types. Maybe I want to have that. Who knows? Or maybe, you know, we are just gonna stick to the you know, different names, different types. I don't know. I usually, because I program in C a lot, I prefer different names for different types, but that's maybe different in other languages. I don't know. Usually I don't do overloading on operators, but that's just because I don't use C++, for instance. Okay, so anyways, here we added these two, like the set and the z function, and we should try to check the number. So if we have a number, we automatically set its type to n, right? However, we should try to see if it's a positive or negative number, right? If it's a positive number, then we are gonna set its type to n. But also it's it it makes sense. What if the user intended to create a z type? Like that's kind of annoying, but it is what it is. So if it's positive, it's gonna be natural. If it's negative, it's gonna be integer. That's the only way I can see it. Okay, anyway, so let's try to do something like that. So let's try to parse the number. So let number is number node dot. Okay, just closed tmux by mistake. So it's value dot on dot I guess clone dot unwrap dot parse, right? And we kind of know that this should work because the way it was parsed. So I don't want to do something else. We are gonna just unwrap it. Like number should have a number inside of number node, inside of the token. It's kind of impossible to get, like it's unreachable. Unreachable, we don't have that keyword. Okay, fine. So we should parse this into an i32 or i64 maybe. Okay, and then if number is greater or equal to 0, we are gonna keep doing this. I guess I'm just gonna have the type, I guess. So if it's greater than 0, we have type n, else we have type z, right? And then in here, I'm just gonna do type, and it's the same thing. Okay, what? Oh, it's type value maybe, because type is a keyword. Okay, anyway, so here we get the actual type. Nice. So if we go into 05 example, and we try to add two numbers like this, let's just parse it. So if we parse it, it parses it correctly. What if we type check it? I mean, operator plus is not defined, right? But that's because we don't include example slash std lib. So it complains that it expected type n but found type z on column 9. So here, oh, I guess it shows us the operator, and then you have to figure that one by yourself. That's kind of meh, but it's fine. Expected type n but found type z. Okay, so I guess what we could do, because addition on z numbers, it's kind of difficult. I'm not sure how it should be implemented. I was just thinking about, absolute value function that would convert a z number into a n number. That's something we can have, but it's also kind of difficult to implement because you would have to do something like for all a in z, if a is less than 0, and we have already that implemented, but the problem is, so if we go to stdlib, the problem is that less than also just works on natural numbers, right? So that's also a thing. So here it would complain that less than doesn't work. How can we define then maybe z numbers? How about, I was also thinking about a function called maybe, so we have successor and maybe predecessor, like pred, and pred works the other way around, like successor, but somehow we would need to stop them. Right, so maybe the pred function, so if we had a pred that goes from, so let's say that from z to z probably, and we would have something like pred of -1 is, so the idea was that successor of 0 was 1 and so on, and then successor of 1 was 2, right? So here maybe I want to go the other way around. That's kind of weird. I mean, it's just because successor like doesn't make sense to work with negative numbers. It's kind of ugh. But I mean, no, I guess here comes the other way around then, maybe, but I'm not sure. And obviously because we need z numbers, we should use the z function here. And here maybe, I mean, you cannot use successor on a z number anyways. It's an interesting question. Because the problem would become with, if we had successor for negative numbers, then maybe it would go indefinitely lower. That would be annoying. But yeah, anyway, so let's just think about absolute value first. So if a is less than 0, if this thing is true, then I should say that abs of a is maybe 0 minus a. And it's interesting here we also need to define minus as a function. And I think just to be right with the types, we need to apply z here. And then for all a in z, we should do it the other way around. Abs a is equal to a, that's the other case, and then abs 0 is 0. That's like the base case. So I mean, this, would be interesting to get this thing to work. But yeah, the less than operator doesn't work on this, right? So, but at least we have successor. Let's just pretend that we are gonna run this thing just with this file. So we have to define basically everything from scratch. So let's go into stdlib. Let's steal the Boolean definitions. And we just have the Boolean definitions. Z, it's something that we already have. And then comparisons. Let's see how comparison would work on the Z numbers. All right, so if we have A in Z, it's still something similar to successor, but but yeah, like we cannot use successor directly because that's for natural numbers. Like regardless of the type of number, I would have to stop at 0 because we just want like a base case for the successor function. I don't think it would work if the function would actually go for all the numbers, because we go from minus infinity to plus infinity, and that's kind of annoying. Like we need that 0 to be like a checkpoint. So yeah, but it's kind of true that this case is true, right? So successor a is less than successor of a. And then this one is also true. The problem with, so let's say we have a number like -1. Well, I mean, -1 would be converted to successor of -2. right? But that's then is the problem. So like successor of -2 and then successor of -3 and so on. So it grows too much. I'm just thinking maybe obs should be like a built-in function, but not sure because it like works on these things. That's kind of meh about it. Maybe we want less than to be a built-in thing, right? Maybe we want less than to be an actual equality check. But then the problem is, what if you define your own set like booleans? How can you compare them, right? You should be able to define a way to compare them. Well, I guess it makes sense how you can do that, right? So let's say you want to define a set with letters, maybe alphabetical or something, and it's A, B, and so on, whatever. And let's say you have a function or something similar to successor. All right, so you could say for all A in alpha, B in alpha, A less than B is equal to true, then here we have the other way, B is greater than A, and greater than is an operator. It's like the same thing as equality. So we would use less than as an operator, and then greater than is the equality check. So this could work, right, if we implement it this way. And we had built-in comparisons. That could be fine. Okay, that's an interesting idea. Yeah, sure, why not? Let's, and then we could say here something like if, oops, if 0 is greater than A, you know, like this, 0 is greater than A, and then A is greater than 0, we have these cases, right, without equals true. And we can implement the greater than operator or the equal operator as some kind of precondition. Okay, then that could work. And this way we would have the abs operator basically, or abs function. But the next thing would be, how do we define, how do we compute minus? That's pretty hard, not gonna lie. So yeah, this one wouldn't be needed anymore then, the successor stuff comparison, because we would just compare them directly. Although it was pretty cool to compare them, like in stdlib, it was pretty cool to use these formulas to compare the numbers, but yeah, who knows? Maybe it is what it is here. So here I would have to apply z on this thing. Here I might do it as well. So maybe it's just the same type on the left hand side and right hand side, and then depending on the type we might have some built-in implementation. Okay, anyway, so what can we do here with minus? So let's take a look at stdlib. Let's take a look at plus. So for plus we just defined it. Let's try to do the same. So let's have z with minus. Okay, this one is interesting. If a is in z minus z, oh, a minus z0 should be a, right? Like this is one of the rules, I would say. But what if you try to subtract two numbers like this? So a is in z, b is in z, and you have something like some combination of these things. I think we need zsuk as a function. Or maybe it has to be predecessor. Like pred of 0 is -1, right? Z0. Kind of annoying. So then what if we had the predecessor of a plus, or I guess minus b? What would be the result here? Or I guess it's better said if you have a minus predecessor of b. This would just become predecessor of a minus b, right? It's we just transfer -1 from one to the other. And then at some point you are gonna get z0 and something with pred. I think this is kind of it, but we need this pred function. Right? And what's interesting about this? I mean, it kind of sucks because it depends on the number. But I don't think we need, I think we should have plus here. But we don't have plus defined. This one, it's kind of hard, not gonna lie. So we might even need plus between z numbers. I mean, the first one is pretty obvious. If you have this stuff, it's just a, right? Regardless of the sign. If you are adding maybe we should have a built-in function for negating a number, and that's that. I mean, yeah, I guess it kind of makes sense having a function for negating a number, right? Neg a. Maybe neg is gonna be a built-in function. Right, and for now let's just try to, still have natural numbers, but do it like this. Okay, so we have defined abs, and we need to also define neg as a function, negate. So inside of the type checker, const function neg str is going to be called neg, and the type is going to be z to z because it needs to get z number and it's going to negate it. Okay, fair enough. Okay, so let's also add this function. So the neg function from z to z right? So that's that. I think that the rest of the type checking, we shouldn't do anything. Let's try to type check this thing. So I'm gonna type check like this. And now it complains where? 05. It complains on line 4, 30 something. So I guess I have to do z here. Oh, that's annoying. We might need a function that converts from z to n, and abs just converts from z to z, because we cannot express it easily here. Or I mean, it can still go from z to n, but we need this like n function to like typecast it. Right, and let's say n just converts the types without doing anything special. So for instance, if you would give this one a negative number, it should have a runtime error or something. Right. So maybe we need this function. Interesting. And you know, here can be like any, but we don't know how to do that yet, so we just do it like this. So z end to end. I think it's maybe a good idea to have a function that converts the types. Sometimes you need it, I guess. So we need here n, and we convert from z to n. Okay, let's type check again. So now type checking should work. Okay, perfect. Okay, fine, fair enough. Let's see now. What would happen? So if we go into solver, we have some to do still. So here, I don't know how to implement this one, honestly. This one's as well. Weird, we should have inside of proof, we should have some kind of so here if we have a relation, we just apply the mapping. Relation node has some kind on it, so we don't take into account the kind of the relation. Interesting. I mean, yeah, sure, why not? So proof relation, and for proof relation we just check that the relations are equal, or at least we're doing a star until they are equal. 0.5. Interesting. And why not? Let's just try to evaluate it and see what happens. Do I have some prints? Not really. 149. Invalid digit? Because I parse U64. Okay, so if I do substitute built-in, let's say we parse I64, and I mean, here we have some cases. Right, based on the type. So let's say match expression node. Do I have type node? I have type node dot clone dot unwrap. So let's take the type node. Let's have type node. So this would be the type node. Types dot first. So we should expect the first. Do I even have to do like clone unwrap dot value? Oh wow. No, I think I have to clone unwrap just the end. I mean, it's insane, but yeah, it should work. Maybe I just match on this thing and we have something like type n. Let me just do as ref. So we have type n and we do something, we have type z and we do something else. And if it's any other type and you have a number, then it's kind of a to-do case. I don't know how to handle it yet. Okay, so if you have a natural number, we are just going to keep the implementation as it was, right? So we just take the value, we parse it as a U64, we do this whatever type node, this one, this one, this one. Interesting. I don't think I want to randomly apply neg on a number or z function on a number. I think that's kind of a no, maybe, I don't know, right now. Maybe we'll do, I don't know, we'll see. Anyway. So if we have a z number, right? So if we have something like -1, what do we want to do for this thing? We don't have a successor function, so we are not going to do anything on that. If we have a 0, it's not possible because we could have a 0, like, yeah. But it's like straight up a single number, so that's what I'm thinking. Yeah. So what can we do on this number? Don't think we can do anything. So just leave it. Wait, what? Yeah, but obviously it's not used. It's like yeah, not sure. I don't think we it's because I don't include it. Okay, type z. Yeah. And yeah, I don't know what to do here. We'll see, maybe we have to do something. But for now, let's leave it like this. So we are able to parse it. Then if we have functions, right, we can do more interesting stuff. So here, for instance, if we find a successor function, we do something. If we find, so let's change this to a match. Function successor. So if we find a successor, we are gonna do something. If we find function, let's say function n, we are gonna do something. So for function n, here we want as a ref. Yeah, sure, why not? If we find anything else, then it's a to do. So if we find function n, then we need to make sure that the type of the number is z. But the thing is, we already know that it's type z because we did type checking. So we know it's type z. So we should just convert it to a number. So what this function is gonna do is we take the first argument. Let's just copy paste this part and let's fill it in. So we have a number as the first argument, right? We take its value, blah blah, we parse it into u64 because we know it should be u64 if you use n function, or at least it should, yeah, that's gonna turn it into the runtime error I was talking about, right? Then you get the number and you add this thing, but we don't do +1, we just do the value, right? So this function called n is just gonna give us the node, then we have a substitution, and here I guess we just put the implication. Fair enough, fair enough. Okay, so this is the n function. Let's see now, the other ones are z and neg. So for the z function, we know, it's kind of funny, we should have, so the z function converts from natural to z, so it should have u64, like it should be u64, doesn't make sense otherwise, but we create it with type z here. Then we do the substitution, implication, whatnot, and that's that. So this is the z function. It just changes the type. And I guess the last one should be negation. Here we should parse an i64. Type is gonna be z, but here we need to do minus value. So we negate it basically. We want, okay, so here we need to add function neg, function z or whatever. So we have function z, it just converts the type. Function neg converts, keeps the type the same, but it negates the value. And I think that's that. Right, so we have the n function, successor, z function, and negate. We could try to play around a bit with them until we actually try to implement something complicated. So for instance, what would -1 eval do? -1, that's cool. What would neg -1 evaluate to? 1. Okay, so that seems to work. What if we try to apply n on this thing? It's gonna fail because of the parse. Maybe we want to catch these things into a runtime error, but that would be, changing all the unwraps into some kind of error, and then we get a runtime error at the end, right? So that would be cooler. So maybe that's a to-do I have to add on my to-do list, which now it's empty. So do instead of unwraps in solver, maybe we want to return result whatever we have here, and then runtime error, and we implement our own runtime error. It's a good point, right? Because you shouldn't, like, you should be able to do something like negate -1 and then convert it to natural number, right? Even though it was already 1, it was z1, now it's a natural one. It's small details, whatever. Yeah, fair enough, fair enough. So here you could actually add 2 to this thing, and it works, right? So we basically did minus and minus result into plus, but you know what I mean. Okay, fair enough. Let's go back to trying to use our abs function. So abs. Not completely sure if I want abs to return z or n, actually. I think usually you have it return z back, and then you apply n yourself, right? That's how I think it's supposed to work. I'm not completely sure though. I mean, I'm thinking about abs, like the absolute value in complex numbers. There I think you return a real number back. So you still have, yeah, whatever. Anyway, doesn't matter. But for now, let's just pretend that, okay, we have abs. How are we gonna solve these things? Let's see where it fails now. So at line 309, okay, solver 309. So this one is not yet implemented. I guess if you have another kind of function that's not built in, you want to continue. Or I guess you don't want to do anything. Okay, yeah, you don't want to do anything. And it just says no solution was found, right? Because, yeah, we haven't implemented that. So inside of the proof, so let's print here. So print ln. Let's print the relation. I'm not sure if it's printable though. Let's see. So it wants to prove this thing, right? It wants to prove that z0 is greater than -1, or -1 is greater than z0. I mean, the first one is true. Problem is that what we do here with solve a star is that solve a star, we might need to change this thing based on the relation. So solve a star, it just modifies the left hand side until it does something with the right hand side. Okay, so it modifies both of them. Now what sucks here is that we compare equality, right? So we are expecting that the relation from here is going to be always equality, but it's not, because we just added I think 2 videos ago, we added a relation kind called greater than. So that's, not always going to be true. But what I was thinking was that what if you have to minimize both expressions? What if you have to minimize both of them first? Because for instance, here, yeah, it kind of sucks. So relation node, I think we have expression. Did I implemented ORD, which compares them as equal, because that's like it is what it is. I needed that implementation for the priority queue. But whatever. Honestly, we could implement partial ORD for these expressions. I think that could be a nice feature. How did I implement EQ or partial EQ? Don't really remember, honestly. So did I implement EQ on them? I have it implemented like this. Well, EQ makes sense, right? It just checks that everything is equal, so that's perfect. But for compare, I'm not sure you can have ORD. That's the first thing. And the other thing is here when we do the binary heap, let me just do binary heap, and let's have an extra type here. Let's have something like expression weight or something, or weighted, right? And can I define this type? Expression weighted is going to be equal to expression and I32 expression node. You cannot implement stuff on that, right? You cannot do implement ORD for expression weighted. I don't think so. I think you need to wrap it. You have to create a separate type, right? Only traits can be implemented for arbitrary types. So I have to do pub struct. It's gonna be just a struct, and we can make it like this then, right? It still works. Okay, and let's implement partial ORD for expression weighted, and here we are just gonna return std compare equal every time, and here we just return sum, self dot, make it to a self dot compare other. But what is the problem? It needs EQ. So derive background partial EQ and EQ. Okay, this is not needed. Wait, what? Oh, it's ordering equal. Okay. So we just created this structure just to replace the, where was A star? So here, for instance, we just add expression weighted. What do I want? Oh, expression weighted, but it still complains about something. Found struct reverse. So here it's reverse, right? Expression weighted. It was just, I was lazy. Oops, too lazy to create the structure, and I was like, whatever. What do you want here? Too crazy to create a structure, and I just used a tuple, but yeah, it is what it is. Now we can implement our own ORD function. Oh my god, this file is so big. We can implement our own ORD function for expressions, right? And we can use the right one here. So we might be able to do something like let is target is the name of this function, is equal to match relation.kind. Okay, and if it's an equality, then we have this as a function, and if it's greater than, we can just have expression is greater than, right? Yes. Other one still. Match arms are not compatible. What do you mean? Yeah, I mean it's function expressional to boolean. Fuck. Okay. It's just Rust things, I guess. Closures don't have the same type. Or sure did. If you say so, it is what it is. Okay, and the other one is like this. We just copy paste it. Relation kind equality. Okay. And then I guess I can just call this map on the result. Okay. So now we have this extra check here. If we have an equality, we check if the expressions are equal when we do a proof. If we have a greater than, we check that they are greater than. And if we go back to expression node, we have this partial ORD, but Interesting. Problem is that greater than, I mean, it cannot fail really, because it's gonna be either true or false. Simple. Or I guess greater than or anything else. But it's kind of annoying because if the types are different, you cannot really compare them. So we'll see how this one works. What if I don't have ord for now? Let's return none here for the memes. Interestingly enough, oh, this is partial ord. Oh, perfect. So if I return none, I assume it's gonna be false, right? Let's check that. Let's run it and see if it's gonna be false. It looks like it's false, right? If it was true, then some std compare ordering. Let's return greater. Greater would make it work instantly. But I think, yeah, nice. So it applies the first rule because the first rule is true. We forced it to be true. Okay, nice. So it means that none. Okay, perfect. So let's delete this one. We don't need it anymore. Okay, that's, new info for me. It's like the greater than operator uses partial ord. Nice. Okay, so let's match. Should I do self and other like this? Let's see if oh, nice, it generates all the combinations. That's cool. But I'm interested just in number. Let's do, I was curious, what did it generate? Oops. But it is the same name, yeah. Expression node, number node, and expression node, number other. Okay, so this is the important case, and anything else is gonna be none, because it's gonna be none. If you have parentheses, first you open them and then you compare. I don't want to be like that. Like if you have numbers, we know how to compare them in a built-in way, right? I mean, it's kind of annoying because when we do addition, we use the successor function, but when we compare them, it's just, whatever. We just compare them. So what are we gonna do here? We have number, which is a node, right? And number node has a value and a type, right? Should I maybe we should probably match the types. Let type node is gonna be node.type type node. Let's do question mark. So if you don't have a type, then it dies, right? You cannot compare if you don't have a type. Types first, it should exist, and I think this gives me a token. And I mean, if it exists, we should have a value dot clone dot unwrap, like that should already be a thing. But maybe I can even just do question mark as well. Nice. Okay, so let's also get type of the other one. So this is going to be other type. And here I would like to also match type node and type other. And actually, if type node is equal to type other, we can compare the numbers. So I'm just going to parse them as I32. The value, or I guess number node is node dot value parse I64, I guess. Dot unwrap. Do I have to? I think so. 64. Let other node is the same stuff basically, but here other. And then we can just say number node partial compare other node. Other one. Oh, and else it's also none, but here we do return. What do you want here? Should I reference this? Should I just .clone it at the end? I think I have to .clone it somewhere else as well, like maybe here. What do you want? Right? Okay. Whatever. Do I really have to clone it twice? That's nice. Yeah, whatever. Okay, so I have to clone it before calling the question mark. Whatever. So if the types are the same, we just compare them as I64s. Sure. Oh, why not? So that's how we are gonna apply the comparison. Okay, that's cool one. So we get the 1 as the result, as I expected. And here we have something like z0 is 0. It applies this formula. abs1 is negative of -1 because it saw this thing. z0 is greater than a. right? And then it applies this one. Now, 0.5. Problem that we have is what happens if I do eval abs, let's say 2. I have to do z2, okay. It doesn't work, right? And why is that? Well, when it's going to check this proof, the A star thingy solves just the left hand side. It doesn't solve the right hand side. So it's gonna minimize this one and then it's gonna compare it with this, but it doesn't work. So yeah, that's kind of scuffed. I wonder how we can fix it. Okay, so let's go into the solver, and as you can see, the problem here is it only solves the left hand side. What if we also make it solve the right hand side? Or what if we first of all solve the right hand side using this one, like we solve it, right? We get the solution, and then we apply this proof, right? Like we should try to minimize both formulas first, like both the left hand side and the right hand side, and then try to compare them. And that would be a good way to prove. Let's see, so if I add this thing here, right, and the expression is gonna be relation.right, this is gonna give us result, which is vec proof, expression node, which is the result, and solver error, if is the case. So we should put like a question mark. This is gonna give us just the proof steps and the expression node. Okay, interesting. So this is gonna give us let steps, or I guess right steps, and the right expression, right export, right, the right steps, the right expression, and maybe we want to use right export here instead of that. And I can see here we get the steps, so maybe I want to include these right steps somehow. I'm not sure yet. Let's see if this helps. So it did. Nice. So it applied abs z2 is equal to abs 2, so it converted it to z number, and then this thing is equal to 2 because this. Okay, what if we append these things at the end? So let's do first extend. No, but I don't want to extend. I want to vec, do we have concat or cat? Rust concat to vex. What is the best way to concatenate to vex? Append, but it wants to be mutable. Let's make it mutable. So we have concat. Concat is concat from Haskell, okay. So it just does flat map. So append, append right steps. Wait, what? Oh, it also deletes so we can just declare it as mutable, then we can append right steps, and then we can just return steps, right? What do you want? Mutable. Okay, so this should give us all the steps, but I don't think they are in the right order. Let's check. Oh, actually they are. Nice. So basically we know that, so these are step by step, right? So we get abs z2 is equal to abs2, then z0 is equal to 0, and then knowing these two things, we can apply this, right? So that's how you can think about it. Like knowing all the previous steps, you can apply the next one. And it kind of makes sense. It's pretty cool. Let's go back to 0.5 and let's try to have a more complex statement. I mean, you can do that. It doesn't care. Oh shit. Plus only works for natural numbers, sadly. So you could do abs -1. And then you would have to apply n, as I said. Right. It's kind of cool. It gets the solution, so that's nice. Nice. So yeah, like implementing plus would be a challenge, I would say. How would you implement addition on Z? That's a cool question. Let's look back into stdlib. So now that we have comparison, right, we can actually just define comparison in terms of our stuff. So we can say for all a in n, b in n, or I guess I have to do for all b in n, if b is greater than a and a is less than b is equal to true. All right, so we can just switch it. Now we have Fibonacci numbers. Let's test conditions. All right, so it's only one step now, which is kind of meh for me because like for addition we are doing all of this stuff with successor and whatnot, but for comparison it's way too simple. We'll see. Maybe, you know, in the end we won't want to have all of this complicated stuff. Maybe in the future we want to have just a simple, you know, 5 plus 5 is equal to 10. We don't do all the intermediate steps, but yeah, I mean, I'm still quite happy with the results. I mean, we have z numbers now, but we have to implement addition on z numbers, which is kind of hard. Let's have define plus I mean, we can even have, wait, let me check the Lexer. CH something, it was CH something. I'm fucking gonna sneeze. Oh my god. Okay, anyway, so is symbol, right? So we can have plus, maybe with a symbol on top. Let's do ampersand for floats, or I guess for z numbers for now. So how is plus gonna work? Yeah. Not quite sure, honestly. It's, I mean, 0 plus a is gonna be a, that's, I'm pretty sure about that. Honestly, let's try to implement it. I mean, even if it's not gonna work, because I don't know how to implement z plus right now, let's try to see how operator overloading can be implemented, right? So right now it should say that plus is redefined. So it's 0.5, sorry. What the fuck? Why does it show it so many times? Operator is already defined. So it bugged. Okay, fair enough. It's weird that we get this error. So instead of type checking, oops. Why did it go this way? Let's see, where do we define things? So we probably go through the defines, right? And we do the following stuff. We check if we have a certain name. If we do have it already, we push an error, right? And then, okay, so maybe we can try here to have a string and a vec of strings, right? And this way we can maybe map things like, let's say, the function name and the input arguments against the definition node. However, if we do that, we should also change it here as well. So vec string. And I think I'm just gonna use a vec of strings because it's gonna make it easier. So vec okay. Obviously, I guess if we have a set, we want its type to be an integer, or maybe we don't even want a type at all. Let's see how we can do this one. Huh, interesting. Because here when I'm gonna search for a type, the problem that I see with it is we search if it contains key, but what's the type argument? So when I do a def, I guess I handled that. So yeah, we're just gonna have an empty thing there. Okay, anyways, so for a function, we're gonna have a vec, and we just have the input type. So we have only z. So we have type z to string. Right. Then for successor, oops, we have n. For the z capital thingy, for the z set, we have an empty vec. For this function z, we have oh, it was fine with n. And then we have neg function, which goes from z to z. Okay, perfect. So when we go through the defines to check for redefined stuff, right, we have the name of the thingy, but here it's I mean, it's kind of important to know what you are dealing with beforehand. So maybe it should be a match before we do error push. So it should be match define. If you have a set, we just check for the name. If you have a function, if you have an operator, I think that's how it's supposed to work. So I think we have a match on the define. And if you have function, operator, and set. For a set, if the type checker contains key with name and empty vec, then it's redefined, right? So we can just push redefined error. But we don't need the entire thing, we just need this. All right, and then obviously can insert is false. Okay, if we have an operator, we should check if we have obviously the name of the thingy, and as the types we should have node, we should have something like node type node dot types index 0 for left hand side dot value dot clone dot unwrap. So this would be left hand side type, or I guess left type, and let right type is equal to kind of the same thing but with a 1. So here we can do left type and right type. Maybe to make it easier for us, we could keep them as tokens. So here we can do token, because token is anyways hashable. So that could make it easier, my opinion. So for instance, I could just copy paste this as that, right? here maybe. Or here. But here it's Z, and the last one, there's no last one. Okay, perfect. So here, instead of doing all of that unwrapping, we can just leave it like this. I think it's a bit less code to write. Okay, if we have a set, I already said that, and if we have a function, oh, but here it's a defined operator. We can do something similar. I think we can maybe copy paste some stuff. Good, this one, split last, is a good function. So here we have function type and archetypes. We have node dot types, or I guess type node dot types split last, and we should get token, which we don't really care about, and a vec of, I mean, kind of vec of tokens, right? Vec from, I guess, archetypes into. Alright, so we check if it contains this key, and here we say redefined function. Okay, I think that's better. Then this one we can get rid of it. We do this part, and here we are gonna insert. And now this one is interesting. What I'm actually gonna do is not do this insert here, but I'm gonna do them here. So on the else case, basically. Alright, so I'm not gonna do can insert anymore. We're gonna do insert, and the key is gonna be archetypes into, and then define clone. Then here on the else case, no more can insert, that's good. We are gonna insert basically this vec. Shit, what? I assume it wants this to be cloned. Probably this one. Let's do let arg types. Let's delete this into this, and then we can, you know, do clone just here, basically. Archetypes. Do I even need to clone it though? Oh, what the fuck? Clone it here. I'm not sure if I need to clone this. I do. Nice. Okay, and the last one. Is here. I don't even need a node. But wait, where does the name come from? Ah, I did like that with name. Okay. Fuck. Yeah, sure. Why not? But here, I needed a node. Okay, yeah, makes sense. Here I don't need a node anyways. And here it's an empty vec. Okay, whatever. So this should work. Okay, so Here when we check if it contains key, we should just add an empty vec. This is for types. Alright, we check if the type exists basically. Here, we don't need to do anything. For a number, for a literal, symbol is gonna be a string and a vec token. So I should do something like symbol, and this is the type. But since we don't care about the type, we are just gonna do it like this. And yeah, we just use the name as the type because it's a set. And I remember something weird I saw somewhere. Here, this should be a type, I think, for Z and for N. I don't know why I made them identifiers. I don't know. Anyway, so here when we check expression, we care about the symbol, right? When we have variables, don't really care. When we have function, here we need to get back the idea with first we iterate the arguments. First we iterate the arguments. We also have archetypes as a vec. So the type of the arguments, we don't need I, we don't need to enumerate. We just need the argument. We check the expression, we append the error. If we don't have a type, it means that we cannot find the function. So can find is true, can find becomes false. So if one of these check expression fails, it means that we don't know the type of the argument. And if that's true, then we cannot find the function in our list because we don't have the full type. So we cannot do extra checks. But anyways, so the last thing we need to check is if let some archetype is archetype types dot first. So we check if we have a single token type, right? If we have something like that, we need to append that type into archetypes. So we need to do something like archetypes dot push archetype dot value dot clone dot unwrap. This is like unreachable code basically. Okay, I don't know about this one. We might just show a different error instead of this. Okay, so then we need to take the name of the function. We search for it in the symbols. In the symbols we cannot have overloading, that's kind of sketch. Otherwise we need to check the defines. We need to search for the name and we need to add here arg types. I think that's all we need to do here. Oops. Archetypes. Do I need to clone it? Found vec string. We don't even need to, we just push the argument, but we need to clone it. Nice. So we found basic, so here we match that, right? So we get a function node, and if we have a function node, then we know So if we have a function, then we return the type of that function. Okay, so we got the type of the function. It means that the type is matching. Otherwise we say something like undefined function, but here I might also say that it is undefined for the current args, right? So here I should say something like kind of the same thing though, honestly. And here it's like, okay, we couldn't find the function, for instance, imagine plus, that adds natural numbers and integers. We cannot find that. So probably have wrong arguments. Okay, so then we have, let function type is equal to function type the types dot last. So we take the last one. Let's unwrap. And I think I have to do that. Yeah. So the errors for the function are wrong at this point, but we'll have to fix them. Okay, so how about the expression? It needs to be kind of similar though. Let's put it here. So we have to do left type and left errors. We check the expression, the left hand side. We append the errors. We need something similar to archetypes and can find. So obviously if we have errors, then we cannot find. I mean, if we have errors, yeah, it doesn't matter. If where is the code here? So if we have the type correct, we just want to do something similar. So if let some left type is equal to left type dot types dot first, then we have to append it into argument types. Argtypes dot push left type dot clone. Thing like this. Otherwise we cannot find it. Else can find is false. Although I'm not sure what I can use. I'm not sure what I can use can find for, but yeah, it is what it is now. Let's also do the right type. The fuck here. So the right type, same stuff. However, here we have also if let some right is equal to right type dot types dot first, then we push the right type. And then obviously we have this else case, but not sure what we can do with it right now. Okay, so I'd say this part is done, we don't need it. So what we need to do, we need that operator, the name basically. So let me just copy paste this one with name, and we need it here. So operator node dot operator dot value dot whatever. So we have operator type symbols dot get name, and in here we have name and archetypes. Right, we search for the operator. If we find it, we get the type. Otherwise, we push the error. Okay, let's see again. Why do we check expression again? Not sure exactly why we check the expression again. So first of all, we check the expression, left hand side, right hand side. Then we check if we can find the operator that satisfies those conditions, like those types. And here we just do types too. So the left hand side, the right hand side, and here operator type. Yeah, I think that's fine. What we can find, I'm not sure yet how I can use it. So I'm just gonna leave it out. So yeah. Okay, and for parentheses, it doesn't matter. Check statements. We shouldn't have anything special left. So I think that's the only part that's kind of special, let's say. Let's check if it still works. So it still works like usual, doesn't have any errors. But if I define plus for z numbers, will it work to still have no type checking errors? It does. What if I do 1 plus 1? It applies the one with n, right? What if I do z0 plus 1 plus minus 1, let's say, just so it applies the one with z. So we just got operator overloading. That's pretty cool, not gonna lie. So obviously, like in a more normal language, you would probably do it with tables, right? You have the functions and the objects in tables. It's like from the OP language that we developed like 1 year ago, the cool language it was called. That one had operator, or I guess function overloading, but it was, you know, for classes somehow, and it had tables, like a data structure specifically made for OP. But yeah, I mean, I'm happy with this idea, honestly. You know, surprised that we actually got it to work in the end. So, you know, the idea was pretty straightforward. We have a mapping with the key being the name and also the type of the function, like the input type. Let's not, we don't add the output type, right? The output type is outside of this mapping. So we map the function with the arguments to the, like, the rest of the stuff. That's the idea. We map the inputs to the outputs, basically. So that's how we implemented this operator overloading. You know, obviously, if we run the checker is not gonna work because we have different errors now. The errors are gonna be a bit different, but I'm gonna handle that on my own. You don't need to waste more time on that. So yeah, I think this was the important part, right? Like the error, what the error displays, that's not that relevant, right? Like maybe just as an idea how I want it to look like. So this is just the arguments. We don't have anything here. Maybe if this one fails, we have to skip something. I'm not sure what to skip, but we might have to skip something if this fails. Okay. But here, if we don't find a function, what's gonna happen is that imagine we have plus, right? So we have plus that works for z and z, so for two z's, and we also have plus that works for two natural numbers. If we try to add z with natural number, it should say that it couldn't find a plus that matches that overload, or how it does in C++, how the same error from C++. Here it just says plus is not defined. That's okay, but I want it to also say that plus is not defined for z and n, right? That's what I wish it displays here. Then for the operator, the same stuff. Here I want it. Oh, actually that was the operator, but you get the point. The same for functions, right? So here, instead of just undefined, I want it to also say the type of the argument. So we don't have an operator for these types. Maybe show the operator for the... No, we're just gonna say that it doesn't exist for the given types. You have to figure it out on your own. But I think that's that should be all for today. So yeah, that's kind of cool. We actually got some advancements. We managed to implement z as in integers, right? And we did some operator overloading. We don't have plus yet fully implemented for z. That would be, my next goal. Probably will try to implement it on my own or something. But yeah, I mean, we got absolute value. Yeah, still quite a few things done, honestly, so pretty cool. And important part, the rest of the code still works, probably. Yeah. So yeah, this was all for today, and let's see in the next one. So until then, see you.